I'm Rakshita from CSC AML Section C. My course title is Matrices and Calculus. The topic is Jacobian for stress strain in orthotropic materials. Let's get into the topic. Orthotropic materials. An orthotropic materials has unique mechanical properties along three mutually perpendicular axes. Example: longitudinal, transverse, and radial. The examples are wood, unidirectional fiber composites, rolled metals. Key features are properties like stiffness, SE1, E2 differ based on direction. Symmetry possesses three planes of symmetry. The use of the Jacobian matrix for stress strain transformation under coordinate rotation in orthotropic materials provides a robust and systematic method to handle complex material behavior. By applying the Jacobian, one can accurately transfer stresses and strains between different coordinate systems, ensuring that the material's anisotropic properties are correctly represented. This method enhances precision in structural analysis, particularly for composite materials, layered laminates, and other orthotropic engineering applications. The study confirms that the Jacobian approach is not only mathematical rigorous but also computationally efficient, making it suitable for integration into finite element analysis and other numerical methods. The axis misalignment problem. Global versus material axis. In engineering applications, the loading directional global $x and $y often does not align with the material's principal fiber direction. Material axis $1 to $. Fiber matrix. Global axis X and Y. Load direction. To analyze stress, we must mathematically reference frame using transformation material by Jacobian. The Jacobian as a rotation matrix mathematical foundation. The Jacobian matrix J represents the linear approximation of a coordinate transformation for a pure rotation of axis by angle theta. J equals to dou x by dou x, dou x by dou y, dou y by dou x, dou y by dou y. Rotation matrix R. In the context of linear elasticity, the Jacobian is exactly the rotation matrix R. It maps vectors from one basis to another. R equals to cos theta minus sin theta cos theta. The matrix is orthogonally R equals to R. Future scope. Extension to nonlinear materials. The methodology can be extended to study nonlinear or inelastic behavior of orthotropic materials, including plasticity and velocity. That the use of Jacobian matrix for stress strain transformation under coordination rotation in orthotropic materials provides a robust and systematic methods to handle complex material behavior. Automation in computational tools. Incorporating the Jacobian based transformation into FEM software for automated accurate stress strain computation in rotated coordinate systems. Explicit form of T. Transformation matrix T. T equals to C square S square S square C square CS minus CS 2CS minus 2CS C square minus S square. Use it to transform global stresses sigma x, sigma y, tau xy into material stresses sigma 1, sigma 2, tau 2. Inverse matrix t of minus 1. T inverse equals to c square s square minus 2c square c square s square 2cs cs minus cs c square minus s square. Simply replace theta with theta since sin theta minus sin theta. Strain transformation nuance. Engineering versus tensor strain. Critical detail. Engineering shear strain gamma xy equals to 2 epsilon xy. The factor of 2 creates a discrepancy when using a standard T matrix for strain vectors. We use the Euler matrix R to adjust for this factor in Voigt notation. Local stiffness matrix SQ. Matrix coordinates 1 to 2. In the local frame aligned with fibers, the relationship is simply we use engineering constants E1, E2, nu12, G12. Stiffness components Q11 equals to E1 by 1 minus V12 V12 V21. Q22 equals to E2 by 1 minus V12 V21. Q66 equals to G12. Transformed stiffness matrix bar Q. To relate global stress directly to global strain, we use the Jacobian rotation matrices to transform Q into bar Q. Q bar equals to T inverse Q T T inverse T. This operates fully accounts for the coordinate rotation theta. The, the resulting bar Q matrix is fully populated shear extension coupling occurs. Optimization of material orientation. Using the method to optimize fiber orientation in composites for maximum strength and efficiency in engineering applications. Multiscale modeling, integrating with microstructural models to predict macroscale behavior of complex composites more accurately. Dynamic analysis, applying the Jacobian based transformation in dynamic loading conditions, example vibrations impact to predict stress and strain evolution in real time. Optimization of material orientation. Using this method to optimize fiber orientation in composites for maximum strength and efficiency in engineering applications. Analyzing workflow. Define axis, calculate Q, transform and solve. First define axis. Identify global X, Y and material 1, 2 axis and angle theta. That calculation. Compute stiffness in material coordinates using E1, E2, G12. The transform. Use T Jacobian to calculate bar Q for the global system. Solve. Apply global loads to find global strains. Sigma bar epsilon. The use of Jacobian matrix for stress strain transformation under coordinate rotation in orthotropic materials provides a robust and systematic method to handle complex material behavior. By applying the Jacobian, one can accurately transform stresses and strains between different coordinate systems, ensuring that the material's anisotropic properties are correctly represented. This method enhances precision in structural analysis, particularly for composite materials, layered laminates, and other orthotropic engineering applications. The study confirms that the Jacobian approach is not only mathematically rigorous but also computationally efficient, making it suitable for integration into finite element analysis and other numerical methods. Extension on nonlinear materials. This methodology can be expanded to study nonlinear or inelastic behavior of orthotropic materials, including plasticity and viscoelectricity. And the final is this element rotated MP. The rotation is 180 degrees rotation about x-axis. Dynamic analysis. Applying the Jacobian based transformation in dynamic loading conditions, example vibration impact to predict stress and strain evolution in time. Thank you.